Alright, continue. Okay, so that is y of 1. Okay, is 1. So how about y of 1 is 0. Okay, so what's y prime of 1? So first we need to figure out what's y prime. So derivative of e to the 3 over 5x is 3 over 5 times e to the 3 over 5x. And then this guy, we actually need product rule. Derivative of the first guy is just c2, and then the second guy plus the first guy, derivative of the second guy. Okay, so now we can plug in y prime of 1 is 1. So that's c1 3 over 5 e to the 3 over 5. And here we have c2 e to the 3 over 5. We plug in 1, so we have c2 3 over 5 e to the 3 over 5. So that's the same as 1 is c1 3 over 5 e to the 3 over 5. And here, that's c2. And we can see is 1 plus 3 over 5 is actually 8 over 5 e to the 3 over 5. Okay, so how do we solve c1 and c2? Okay. All right. So we build a matrix. Okay, the first we have e to the 3 over 5, e to the 3 over 5, 0. Okay, second we have 3 over 5, e to the 3 over 5, 8 over 5, e to the 3 over 5. That is 1. So far, so good, everybody. And we can simplify. So we can multiply by e to the minus 3 over 5 into r1. Okay, then we have 1, 1, 0. Okay, and we can also do the same thing. Okay, so we can multiply by e to the minus 3 over 5 in r2. Then we have 3 over 5, 8 over 5, and this is e to the minus 3 over 5. Okay, and let's make action form. So let's cue this guy. So what do? Use negative 3 over 5 r1 add to r2. So we have 1, 1, 0. This guy is 0. And then next we have 8 over 5 subtract 3 over 5. That is 1. So 1 is e to the negative 3 over 5. Okay, so this is c1, c2, right-hand side. The last row tells us that c2 is e to the negative 3 over 5. And then when we plug in the first row, c1 plus c2 is 0. So c1 is negative c2, which is negative e to the negative 3 over 5. Eventually, y is c1 is negative e to the negative 3 over 5, and e to the 3 over 5x. Plus c2 is e to the negative 3 over 5, x times e to the 3 over 5x. Alright, so far so good, everybody? Okay, so that is example 7. Alright, so we finished the 2 distinct real root case and 1 repeated real root case. The last case is when we have 2 complex conjugate roots. Okay, so we have the characteristic equation, and because it's negative, we're gonna have 2 complex roots. Okay, so how does work? Alright, so this 2 complex roots we can still think about is like 2 roots, right? With r1 is like alpha plus beta I, and r2 is like alpha minus beta I, right? And our solution is C1 e to the R1x plus C2 e to the R2x. So R1 is alpha plus beta I. So that's why you have e to the alpha x times e to the I beta x. And then the other one, you have e to the alpha x times e to the negative I beta x. What does this mean? What is e to the ix? Well, if you can remember the Taylor series extension from Calculus 2, okay, what is that? The function is approximately by the Taylor series, okay? And the Taylor series converges to the functions in the interval of convergence. And the Taylor series is the sum of the nth derivative times x minus x0 to the power of n over n factorial. Okay, and what is the Taylor series for e to the x? So e to the x, the Taylor series is I from 0 to infinity of x over x to the I factorial. Okay, so maybe I should not use I, let's use k, because I don't want to abuse notation. My I here means the complex number I. Okay, so k from 0x to k over k factorial. Okay, so that's why now you just replace x by ix. So when k is 0, you get 1. Okay, when k equals to 1, you get x. When k equals to 2, you get x over 2, and x3 over 3 factorial, etc. So that's why here, when you replace x by ix, you get ix here. But here, because I squared is minus 1, you get negative. And then the next term, I cube, is actually minus I. So that's why you get minus I. Okay? And then I to the 4th is actually become 1. Okay? And that's why this is what we get. If you look at the even power terms, group the even power terms together and group the odd power terms together, and I don't know whether you can still remember. So this is actually the Taylor series for cosine, and this is actually the Taylor series for sine x. Okay? So if you don't remember, it's okay. You can email me, or you can go to our course website, and then on the left hand side you can see my Calculus 2. Okay, go to the Calculus 2 course website, and then this Taylor series is in chapter 9, sessions 9.3. Okay, so this is Cal 2 session 9.3. Okay, then you can get the table of the Taylor series. Alright, so we have figured out e to the ix is cosine x plus I times sine x. This is called the Euler's formula. Okay, now magic. You can see our solution. This let me use different color. Okay, so these are my solution, but you can see the exponent, we have the complex number. That's not what we want, okay? But we place e to the I beta x. So because e to the ix equals to cosine x plus I sine x. So when you have extra beta, you just put the beta inside the cosine and the sine. Okay, so we replace it here. And this is negative because sine of negative x is negative sine of x. Cosine of negative x is cosine of x. Okay, let me write it down here. So that's why you can put the negative outside of the sign here. Okay, so a bit funny. Because the original equations, right? Original equation is a y prime prime plus b y prime plus c y equal to 0. Because the coefficients are all real numbers, we expect to have real solution. So is it true that the above general solution can be written as C3 e to the alpha x times cosine beta x plus C4 e to the a alpha x sine beta x? Yes, actually we can do that. We can show that both of them are a solution of the differential equation. Okay, but we're not going to show it here, but you can check that, compute the y prime, compute the y prime prime, and plug it into the differential equations. You can see the left hand side equals to 0, so that's why they are the solution. Okay, so next we get two solutions. We want to show they are linearly independent. Then we can know that the general solution is a linear combination of those two solutions. How do we do that? First row, put down those two functions. Second row, take the derivative of them. So here we do product rule. We have the first guy prime times second guy, okay, minus the first guy times second guy prime. But the derivative of cosine is minus sine. And don't forget we have an extra beta there, okay? And then here we have product rule again. The first guy is alpha times e to the alpha x times second guy plus the first guy times the derivative of the second guy. Derivative of sine is cosine, but you have an extra beta here. Okay, so then the one again is we cross multiply. So this guy times this guy is, let's see. Oh, it's actually here. So it's alpha e to the 2 alpha x cosine beta x and sine beta x. And then this guy times this guy is actually beta e to the 2 alpha x cosine square. Subtract this guy times this guy, right? But because the order is a little bit different. So subtract this guy times this guy, I put it here. So that's alpha e to the 2 alpha x cosine times sine. And then this guy times this guy, because subtract negative become positive, then we have betas and then e to the 2 alpha x sine square. Okay. All right. So what is that? Okay. You can see here and here they cancel. And for this guy, can you see the common factor? Beta e to the 2 alpha x. After we factor out that common factor, we get cosine square plus sine square. And that is 1. So that's why the answer is just beta e to the 2 alpha x. And we know beta is not 0 because we assume it's complex number, right? Complex number plus alpha plus or minus beta I. We assume beta is not 0. If beta is 0, then you have real numbers. You don't have complex numbers. Then you are in case 1. And the exponential term is also not 0. So that's why the one skin is not 0. So that's why we have the two solutions are linearly independent. Okay, let's compute this example. Alright, let me get my black color here. Okay, so first of all, I don't want to see the fraction, okay? Maybe it's okay to leave it as a fraction because complex roots, we're not gonna factor it in terms of like a 2 factor, the product of 2 linear factor. We're gonna use the quadratic formula anyway. So first of all, the characteristic equation. When you see y prime prime, we place that by r squared. When you see y prime, we place it up by r. When you see y, and that will give us the constant. Okay, so r is 2a negative b plus or minus b squared minus 4ac. Oops, they cancel. Do you know what is 16 minus 25? Yes, that is negative 9, right? Square root of 9 is 3. Square root of minus 1 is I. Okay, square root of minus 1 is I. Alright, so we get negative 4 over 2 is 2 plus or minus 3 over 2i. So this guy is like the alpha, this line is like the beta, and then after we figure out the alpha and beta, we just use the formula. The formula for two complex roots is c1 e to the alpha x, so negative 2x, and then the beta is just going to be cosine and sine. So cosine beta is 3 over 2x plus c2 e to the alpha minus 2x, and then sine of beta 3 over 2x. Okay? Yes, so we just use the formula, and then in order to figure out the C1 and C2, we need to plug in. So 5, 0 is 2. So let's plug in. What's cosine 0? 1. So we have C1. What's sine 0? 0. Awesome! C1 is 2. We get it for free. And then y prime, what's y prime? It needs more work, right? Product rule, derivative of the first guy, minus 2 c1 e to the minus 2x cosine 3 over 2x plus first guy, derivative of the second guy. Derivative of cosine is minus sine times 3 over 2 plus still product root, derivative of the first guy, that's minus 2 c2 e to the minus 2x sine of 3 over 2x plus c2 e to the minus 2x, derivative of the second guy. Derivative of sine is cosine times 3 over 2. Alright, so we know y prime of 0 is 1, and we know c1 is 2, okay? So 2 times 2 is 4, e to the 0, 1, cosine 0, 1. Sine, when you see sine, oh, so happy. The whole term is gone because sine of 0 is 0. Here, sine of 0 is 0, yay! And then the last term, we have c2, e to the 0 is 1, cosine 0 is 1, we have 3 over 2. Okay, so move the 4 over, we get c2 times 3 over 2 is 5. So c2 is 10 over 3. Do you get that? So don't forget the last steps. C1 is 2, e to the minus 2x cosine 3 over 2x, and then plus c2 10 over 3 e to the minus 2x sine 3 over 2x. Okay. Alright. So that finished the problem. Summary. So today we talk about how to solve second order linear differential equation with constant coefficients. And we have two cases, okay? So first of all, you gotta figure out what is the characteristic equation. So the characteristic equation okay, so the characteristic equation is so okay. Characteristic equation is AR squared plus BR plus C equal to 0. And then you want to solve for R. So R, we have the quadratic formula. And then depending on the discriminants, we have three cases. 2 distinct real roots, 1 repeated real roots, 2 complex conjugate roots. Okay, the first case, the formula is just c1 e to the r1x plus c2 e to the r2x. The second case, we're gonna have still, because you see this guy is the same as this guy. So we have c1 e to the r1x, but the second root, you don't do the same thing. Okay, you cannot just put e to the r1x here. You have an extra x in front of it to make them different and linearly independent. And then the third case, we have 2 complex conjugate roots. Okay, and the solution is going to be this and this, but we are actually able to express our solution in terms of real solution. Because we're given the differential equation with real coefficients, we kind of expect our solution to be a real solution as well. So you use this formula. Okay, so I put C3 and C4 because I just want to indicate the C3 and the C1 are not the same. C2 and C4 are not the same. But when you solve the problem, you just directly use this one. You can call this guy C1 and C2 instead of C3, C4. Okay? So you use C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. So that is the formula. Okay? So this is how we solve second order linear ODE with constant coefficients. You figure out the characteristic equation, and then you figure out the roots, and then you just pick the correct formula. However, this formula will not be given during the exam, so please try your best to memorize them. But actually, you can kind of understand them, right? Okay, good. Have a nice day. Bye.